But for the purposes of midterm, all you're gonna be doing is applying your own difference. So I guess we'll start with like the general form. Don't want to make another mistake. Maybe I'm writing this in a form that's less familiar, but does anyone know what the B system means? It could, but usually we write, yeah, it's something like it's extensive property where B is just little b times m. Extensive just means it's so it depends on what you have of it. Or let's say our big B is m. So we have m times b. So our b is just 1. So if we have the material derivative of mass with respect to time, what is that? If this is just m. Just this guy. What is this guy if this is m? No.
0.
0. Because the mass hasn't changed in the whole space and time. So I'll rewrite this for math. And this is equal to 0. And then remember that B is just mass times little b. So if this big B is mass, what's this little b? 1. Maybe it was confusing to write in terms of like the little b and stuff, but maybe this is much more familiar for you guys. Yeah. So we have 0 is equal to this funky looking term plus this funky looking term. Let's try and like parse what this means. We have the time derivative of some integral over some control volume of rho dv. For the purposes of this class, like I said, rho is a constant, so I can always just take rho out of this integral. So what am I left with? Del t of rho of the control volume dv. The integral of dv is just v. So this is just equal to del t of rho v. And what's that? Someone said it earlier. Mass flow rate, yeah. For those of you that find this unfamiliar, this is just, so the derivative rho with respect to time since it's constant, so that's just rho. And then v dot. What's v dot? Yeah, volumetric flow rate. Rho q, which is equal to m dot. Any questions on that part? Yeah. The material derivative with respect to mass in the system isn't changing. So it's 0. Conservation of mass. Yeah, I guess another way of saying this is that m dot in plus m dot out equals 0. Yeah, that's fine. All right, so now we parse this guy. What's this guy? So we're gonna get rho outside the integral again. We're gonna get velocity dotted with normal, so we're gonna get some velocity dA. What's the integral of velocity dA?
Velocity times A. Velocity times A.
And that is? We said it earlier.
That's flow rate.
It's flow rate. So this is also a mass flow rate term. Because like someone said, this is actually just in the trivial form m dot in plus m dot out, which is this mass contribution. Questions on that? I have explained it poorly, so please don't hesitate to ask.
Yeah, on the right hand side, there's two terms. The first term just talks about how it's just if the mass just in the flow in the actual control volume is just increasing or decreasing, and the second term just talks about the flux. So this, if you think about it logically, if there is more flux out than there's flux in, that term, that rho v dot n, that will be a positive term just by the way the math works. And for it to satisfy the conservation mass equals 0, that left term has to be like a negative number. So what that's physically representing is that if there's more mass going out than there's mass coming in, that means logically the mass inside the control volume has to be decreasing. Yeah. Question?
No. I'm sure you've also seen like situations where like the mass out is greater than the mass in. But if you draw your control volume in such a way that the mass conservation holds, then yeah, you can always draw your control volume like that mass conservation.
This is general form.
Yeah,
Right?
the general form.
You might be about to go over this, but what constitutes like a restricted form?
Restricted form?
Yeah.
Oh, I see what you're talking about. So that's just when we're not really integrating over area, like we're given everything. So we can only just rewrite this as rho A V in. So rho A in plus rho A out V out. If we're able to write it like this, we don't even have to worry about the integration. We can just do mass conservation at that point. Just do it with numbers. But if we don't have explicit expressions for A in, B in, A out, V out, we'd have to use the integration. So that would be like the restricted form when we can write it in terms of scalars.
Okay.
Yeah.
Which one is the expression of the flux?
The second one.
So the first, the m dot is not a flux.
No.
Oh, or yeah, I mean, I guess the way you write it is like, is m in like whatever's inside the control volume? Do you mean? Okay, so it kind of looks like it's like the mass flow rate in coming into the control volume plus the mass flow rate out, not just the rate of change of the inside. So no, there's like, so the flux is what's coming in minus like what's going on, like whatever, like the difference between the two. So that's okay, so think of it this way. So this m in is the whatever's just inside the control volume, how is that changing over time? And the m out is just the net outflow. So that includes the actual flow coming in and flow coming out. So like
That's just the same thing.
yeah, so or think of like a tank of a tank of like water, and then there's just like one like entrance that's like where mass is leaking. Okay, so if you think of the tank as like a control volume, like the amount of water in that tank is decreasing over time, right? So that is that first term, just the amount of that item in your control volume is decreasing. That second term refers to the flux. So in this tank problem, there's no actual flow coming in, but there's flow going out. So there's like this well, it's a positive value over here. There's a positive flux out of the tank, right? So there's a positive flux out, but there's a negative rate of change of water in the tank, right? So when you add those two like rates, it'll equal zero and it'll cancel out. So that is the stuff in the control volume, how it's just that isolatedly changing, and that just refers to how it's coming in or out. So for mass, it's fine. It's like it doesn't really matter. But when for other quantities, something can be independently changing inside like a concentration or something, or like something else can be independently changing inside the tank without it being attributed to an inflow and outflow.
I think it would be better if I have to write this down. What you're saying is more accurate. This is like if I have some control volume that's just changing mass internally. So like mass is, somehow leaving or exiting the system. Maybe it's like water or something.
It can also, for deforming control volumes, that'll also come into play because like the rate of change, it's ddt of the entire volume integral. So if the volume itself is changing, that could also be a way where that first term is like non-zero or like just some actual number. So
Yeah, that's a good way of putting it. Like it's the thing that's coming through the boundary or coming out of the boundary, the control surface. Whereas this is what's internally happening inside the control volume. Yeah,
Yeah, I was just gonna ask, like, since capital D is like property, like mass volume energy, you can just think of that first term of whatever's happening.
yeah, that's probably better. Does that part make sense? Yeah.
you can like add like extra expression just on your equal sign on this side, just saying which talks about like what's just happening inside, because these are the two flex terms, right?
Yeah.
So just like add to
So I'll add it.
yeah.
So this is the flux. And then this is just our like internal inductors.
Yeah.
That's this guy. This is this guy. Usually, you're really only considering the flux.
Yeah.
Which is why I wrote that, but yeah, I guess that's me. Any questions? I'll erase this and write RTT for linear momentum. And I think that's a little bit more complicated, but that's the last thing that was in scope for the ODK. You're not going to be asked to do moment of momentum. Now, I guess I won't explain in terms of the big D, little d thing because it may be confusing. So I'll just write the formula full. I guess there are different cases. So first of all, that was for like, I guess you could say like any control volume, but if we wanted to be more specific, a moving control volume, the mass conservation would be exactly what I just said and showed on the board, except for one small difference. So the difference is instead of V, where V would have been, I don't know, whatever flux was happening, so whatever was leaving, coming to the system, that velocity. Now we're dealing with a moving control volume, so we have to take that velocity with respect to the velocity of the control volume. So that omega is really just whatever velocity was coming in earlier. So our V from before But now we gotta take it with respect to control volume because our control volume is also moving. So that's just a tiny fix. And this is also still equal to 0. That's just the kind of tiny fix for a moving control volume. Any questions?
That's where that big T,
Which one?
next to the.
Yeah, sorry, that is a plus.
So basically, the equation is almost there as before, but it's the relative velocity out minus. relative velocity.
I mean, you could consider it actually to be the exact same equation, just because we're dealing with a moving control volume, we have to deal with a different velocity. Yes,
Or the second term, where you have W equals to V minus V control volume. For the first second G velocity, is that the velocity of our control volume or the velocity of our control surface?
so if you remember, like, if we have some flux, this is still our flux term. If we have some like mass leaving at some velocity v, that's our absolute velocity. This v is our absolute velocity.
It's the absolute is not our surface, but not the control volume.
Yeah, it's a control surface integral, so it's whatever's happening at the boundary. And then if that's absolute, then this CV term represents velocity of the control volume. And then W is our relative velocity. I guess this would also hold for the deformed control volume as well. Yeah. So I'll add this is also for deformed control volume. Because usually when we're dealing with looping control volumes, we don't really have any internal like mass flow. So this term would go to 0. But if it's deforming, meaning like the mass is changing over time, this term would be non-zero, you have to consider it. But it's the same form. I think it's finally now we can get to linear. So time.
That's 6.
So now our equation is going to look like really just the same thing. Except now we got some V in there. Okay, but now remember, like, when I had, this was actually equal to the material derivative of mass with respect to time, which due to mass conservation, it is going to be 0 always, because we can always draw a control volume such that our mass is conserved. But for this case, now our big M is, so our big B is actually going to be MV. So what's this guy equal to? Yeah.
I was just gonna say, aren't you missing a V in the?
Yeah, I am. Sorry. Thank you. Nice. Thank you. So what's? Yeah, I put a V in there. Right.
Yeah.
So so this guy's going to be equal to this guy. For mass conservation, it was 0. What about now? Yeah.
Net force.
Net force. So this is going to be net force, which is also a vector.
Is that W supposed to be a V2 in the, because we're not looking at,
It's
I think that's like, we use W for the relative motion stuff, right? Or is this still W here? Okay. Oh, okay, I mean, okay, in the case that there is relative velocity, yeah.
Yeah. But this is still for moving control volume.
Okay,
I see the confusion. Remember that this omega really only becomes relevant if we have a relative velocity, which means if our control volume isn't moving, we're not gonna have a relative velocity. Everything's absolute. So this omega would be V if we were dealing with like a fixed control volume. So for fixed control volumes, don't even worry about omega, just think about V. For moving control volumes, think about omega. Think about omega and V, I guess, because they're related. I think that's a good rule of thumb. So I guess we could parse this out just like we did for this thing. So I should probably clarify this V and this V don't always have to be the same. This is really tricky and it actually shows up in homework 6, the second question, where this velocity is actually different than this velocity. For the purposes of this ODK, we're not going to deal with such a complicated problem. So as long as you think about this is the flux term, whatever's coming out, and this is whatever is happening inside the control volume, usually these velocities will be the same, and you shouldn't really consider them to be different. But for homework 6 question 2, they are. Any questions before I parse this stuff out? Yeah,
What would be the case when the control volume velocity wouldn't be the same of the control substance?
that's a good question. Homework 6 question 2, like I said. You want me to like do homework 6 question?
No, but like I like did it over today and like I don't remember like what the control volumes like velocity being in the control surface.
Yeah,
Shouldn't that be just the velocity of the fluid and then
The V control volume there, the first case in the question is U, and the second V is V. U is equal to V gets minus V.
so that VCV will not be the same as that V.
yeah,
The CV is the V of the cart, and the second V is the V of the jet.
yes, that's right. But that's like one really difficult case that we're not going to ask you about on the midterm. For most cases, the velocity at the control surface will be the same as the velocity of the control. So let's try and break this down now. So similarly to how we broke down the other one, we have rho V, let's assume that I think VCV isn't usually a function of time or space. So we have this. We have, once again, we have volume. We have rho. And we have now V. So rho V V. So it's rho volume and then velocity. We know what this is, right? What's rho V?
Q.
Just rho V. Mass. So what's this? Delta T of MV. What's MV? Linear momentum. So this is the change in linear momentum. Yeah. So this is the change in linear momentum. If you wanted to write this out, it would be M dot V plus M V dot. Because sometimes these things are changing with time. So just by product rule, you can write that out. Yeah.
If it's like, step 1 to line 2, why can't we factor out for like inputs, see the outside?
Because we're assuming VCV is only a function of time. Yeah. In this case, we're not assuming this is like some velocity field. Like it's just some free jet or some mass flow that's coming in or coming out. And we're thinking about the velocity of the control volume. That's probably just going to be a function of time, like just like kinematic relationships, like Z equals V naught plus AT, that kind of stuff.
Has no relationship with the volume. So
Yeah, we're not like this volume is a function is a technically dx dy dz. So velocity isn't a function of x volumes. Yeah. And similarly, this term, we're gonna get rho v omega dot n omega. And I just want to clarify, since I'm talking about omega here, I am talking about moving control volumes. If it was a fixed control volume, then like Fernand said, this v and this v would be the same. So we have rho v omega times some surface area. So we have rho a v omega. We know what rho a v is. That's just mass flow rate. Now, I want to be clear though, like right now, I'm not considering the sign difference from this. When you write out your control volume, you always have to consider the sign from this guy. Remember that normal is always defined outwards.
Yeah, note here it's outward. It is outward here.
That's where I'm. So normal always defined outwards here.
Yeah.
And then for the other one, it's inwards.
Yeah, for that other just like specific centripetal force thing. But basically, if flow is going out, it's positive. If it's coming in, it's negative.
So let's say, example sake, let's say we have omega coming in this way. So this is our relative velocity. So you're gonna have to think about your absolute minus your velocity CV. Think about the sign of that. Let's say it's going inside. In this case, omega dot n would be negative. So we get a negative term right here. So even though I'm writing plus this, it could be a negative as well. You have to think about the sign. So let's say it is negative, then what we're left with is net force is equal to m dot v plus mv minus m dot w. And if you wanted to check if the units can't match out on both sides, okay. Any questions on that? And I actually should be very clear. This is V of CV. This is omega, so it's defined up here. Questions?
A question.
Yeah.
That W was going outwards, then that negative would be a positive, right?
Yeah, I just wrote that in there for the sake of example. I guess like if we were to like grade some kind of problem like this, we wouldn't expect you to like parse anything out. Like if you were to like just jump straight to this and you happen to get the right expression, I would give credit for that. But if you want to just double check and make sure everything's right, just start from mental transport theorem, understand what each of the two terms mean. Understand if this term is going to be either net force or zero, and just try and go down from there. And maybe that'll get you more hard.
Yeah. If you're super confident, you can go there, but there's I mean, we can't say anything for sure, but like if you're not confident, showing as much of your knowledge as you can was the best way to go for it. So if you just know that expression and you can work from there, that's fine if you're like unsure.
I believe that's all.
All right, so now that's like the basic. Oh yeah, I'll erase this. That's the basic. Oh, that's fine. I'll keep my notes on this later. I'm gonna go with this. I already erased some of it, but I'll be putting some notes on this later.
One question. For the second equation you had, you do this. That one had like a velocity and the other one like didn't have like that velocity.
The second is equation for the
Like the bigger ones won't have like that, the velocity, like the volume.
Yeah.
So if like you had a uniform velocity distribution, then you cancel that frequency out and then you're left with.
yeah. If your entire control volume is moving, then that VCV what comes into play, or like then you have a VCV there. But if it's if like nothing is moving, if it's not like if that frame is not like, accelerating or anything, then like your time derivative then goes to zero then. So in that sense, so that VCV is going to be a non-zero term if your control volume is moving, but it's really going to come into play if it's accelerating, because that's when the time derivative will be a will make it a non-zero term.
Okay.
Yeah.
You have written on the board that, rho A of W is then equal to m dot times W. Isn't the mass flux in related to W and not V? Like, m dot would be rho A times W and not rho A times V.
No. So that V was like in Roman 2.2 would be the example of the fluid of the jet, which is what's coming in. Whereas omega is the relative velocity of the jet with the control volume. So the mass flow rate in would be from the jet.
But say if the cart then moves away at the same velocity, we have no mass flux in. And in that case, W would be zero, which seems more consistent.
Yeah, because I think you might be right. How about we'll revisit that at the end. Is that cool?
Yeah.
Cool. Thank you. Okay. So erase that slightly prematurely. Sorry, but we're gonna go over a few practice problems now. One related to streak lines, or like the entire like path line, streak line. One related to Reynolds transfer theorem, and then you were going over one other question.
I mean, I don't know how much. I mean, how many of you guys have solved Homer 6 questions? That's like less than half of you, so I guess I could go.
All right, that's fine. So we'll say that one for the end though. Okay, so let's first go over a streamline question. All right, let me pull this up. Okay, so suppose we have a velocity field, and make sure it writes properly here. U is equal to A over X. I think that's visible. And then B is equal to AY over X squared. So first thing, and then let's say A is equal to 2. The first thing is that find the streamline. So we'll go streamline first. Streamline, which passes through the coordinate 1, 3. And then the second question is find the time for a particle to go from x is equal to 1 to x is equal to 3. or not 3, let's go 2, right? And then the last thing is find streak line for the same, for a flow passing through the point 1, comma 3. So I'll give you like until 6:20 to kind of get some rough steps into like how you think you're gonna do it, and then we'll just go over it together. Yeah. Okay, so let's just start going over this thing. So let's go to streamline first. What do we think is like the first step, or rather the first equation we should be writing for streamline? Like, yeah, exactly. So let's go with, write it. dy over dx is equal to v over u. And now what we'll do, we plug it in. dy dx is equal to y over squared over a over x. Okay, and then this will now cancel stuff out. Take 1 there, and that equals to, yeah, that'll equal to y over x. Well, yeah. Yeah. So now, again, this is pretty simple setup. Now let's focus on doing a separation of variables. We just move, we go dy over y is equal to dx over x. And then we integrate this from y up to y, and then x up to x. Yeah, it's fine. And then we get what ln of y over y naught is equal to natural log of x over x naught. And then put both sides up to the e, you get y over y naught is equal to x over x naught. And then you put y in terms of x, this gives y is equal to y naught over x naught, x is equal to y is equal to 3x. Right? Does this make sense? This seems like a familiar problem kind of setup. We just put it in terms of, this is your like main equation for a streamline. If you're ever asked to find this, yeah, what's up?
Can you integrate without bounds and?
Yeah, that's also fine as well. You can just do just an indefinite integral, but you get ln or y plus c is equal to ln x plus c over here. And then, well, you can just subtract this one c to the other, and you get ln x plus c. Just go e to both sides, you get y is equal to c x. And then you plug in, you solve for c, you use the fact that you have a condition of 1 is 3. So if you plug in 1 here, c has to be 3 for y equal 3. So you get the same thing, y is equal to 3x. Yeah. So yeah, this is your main equation. Once you get this, just plug in your expressions for u and v. And then you can just do it either this type of integral, or you can do it indefinite. This might be a little more general case. You can just do this and figure out like the value. Cool, that makes sense. Yeah, what's up?
You walk through how, sorry, maybe my calculus skills aren't that good, but e for the natural log x plus e.
Oh, sorry, yeah, I can do that. Because so this is e to the ln natural log y is equal to e to the natural log x plus c. And then remember when you like you have like the sum of an exponent, this just equals e to the ln x e to the I have a little bit of shorthand method of doing this. So this is equal to this thing because you can add exponents, and I just set this as just another c because e to the c is just some other constant. So that's a little bit more of a thought out way of doing that, but yeah. Cool, that makes sense. Okay. I've underestimated the amount. I've overestimated the amount of space I had, so it was the bottom. Second part. So now we need to find the time for a particle to go from this to this thing. Now that there's time involved, you probably want to look at a path line. So the equation for a path line is let's look at x first, because it's asking us to go from x to x1 x2. dx dt is equal to, well, you say u is equal to dx dt is equal to a over x, right? Now the same thing, do another separation of variables. You get x dx is equal to a dt. I think so. And then you do, then what? You do the same integral on both sides, and yeah. In this case, you can do, since you have two bounds, you want the particle to go from x1 to x2. You can set it up. You can actually have a bounded integral, x naught to x1, and then t naught to t1. And then if you set this up, this will become half x1 squared minus half x naught squared is equal to a times t minus t1 minus t naught. And time, so this is just a change of t. And then you get this one. Half x1 squared minus half x naught squared is equal to a change of t, where you have x1 is equal to 2 and x naught is equal to 1. And you have this is equal to this 2. And once you plug this in, what do you get? We can put 2 on the outside as well. minus 1 is equal to 4 That's right. 3/4 seconds is here. Change it to, well, you know, if I did my math wrong or something. Okay, does that also make sense? So you go through your path line equation now. This honestly looks a little bit more like a streamline equation, a streak line equation, but you start off with the same u is equal to dx dt. Again, you plug in what your u is, and in most cases it'll be nice to you. And yeah, what's up?
Oh, just to confirm, you can't do it the other way, right? Because of the long term.
You can. Okay, I'll in the next part of the problem for the streak line, we'll like formally derive the path line equations, and then you'll see how the y will come into play.
Okay.
So, no worries. So then you just do the you plug in your u, you do the same separation of variables. We did bounded this time because you actually have a bound over here, and then once you do that, you can just plug in all your values or these values and then solve for a change of time. So this actually, if you guys know the equation for a streak line, this actually, since you have a bound for time, it actually looks a little bit more like that. So you start off with the same path line equation, but then it's a slightly different way of solving it. But does the logic make sense? Any questions about how we got to that? Cool. If everyone's written this stuff down, I'm gonna erase this section and then we're gonna do part 3. Cool. So for part 3 to find the streak line, in most cases, just start with the path line equation, and then it'll just make it a lot easier to go to the streamline. So this time we're going to do the exact same thing as we did over there. We're going to start with this dx dt is equal to a over x. And the reason you start with this one is that it is a simpler one. There's no like y term, so it's a little bit easier for you to like solve for stuff and do the separation of variables. So now this time for the actual path line, we'll do the same like separation of variables, but for this case, we'll go from like a 0 to x of x dx, and this integral from 0 to t of a dt. And then this will give you where does it go? Or you can just do the normal integral. You don't even have to do this part. Just take this out for now. Just do the integral of that and this, these two, and then you'll get a half x squared plus c is equal to at plus c. Do the same thing, move stuff to one side, like just solve for x. You'll get x is equal to root of 2at plus c. And then you plug in the same, I guess, so, and this is for problem 3 now. So we now have this way over here. So you can use that to say that, okay. And then this will be, for the path line, you can say that this is at t equals 0. Okay, so this question will, let's assume we pass 1,3 at t equals 0. So, all right, so the way this problem is set up, I like added on this like streak line, like part of it to what I'd already seen. So if you actually had a question like this in an exam, to be a little more clear. But let's assume for the purpose of calculating the actual streak line, you knew that it passes at an initial condition at 1,3. And so then you plug this in, you know, t equals 0, this entire thing goes away. So then c is just equal to 1, just based on that. So you get x is equal to root 2at plus 1. Yeah. And then now for y, and now y is a little more complicated, right? Because you have, or the v is a little bit more complicated because you have the y dt is equal to ay over x squared. But now that you solve for x, you can take that, and you can plug it into your dy dt. So you would get something like dy dt is equal to a y over 2at plus 1. Right? Yeah, and now you do a separation of variables again. I'm just gonna skip ahead to the post integral. You will have something that looks like the natural log of y plus c is equal to half natural log of 2at plus 1 plus c. Cool. And now you have to solve for y. So the way I did it was that I set this half to be like the exponent of the inside of this thing. So first of all, you could remove one of the c's because you only have a c on the other side. So then I said e to the natural log of y is equal to e to the natural log of what was 2a t plus 1 to the half plus c, and that'll give you, what is this, y is equal to c times root 2at plus 1. Yeah, and then this will give you, again, if you plug in this stuff here, you'll get c is equal to 3. So then y is equal to 3 root 2at plus 1. Now, does this look familiar? This equation. Like, look at these two. Did we see this earlier in this problem? Like this type of relationship. So what if I plug in, so this is plug in this x for that. You can just say that y is equal to 3x. And that was just the streamline equation, right? So since this was steady state and you were passing through the same point here, you were able to, well, like re-derive the streamline equation basically. So if any time if you saw like a pattern like this, where you're like, okay, I know this x is over here, and it's passing through the exact same like point, you can, and then you found the streamline is a lot easier to find. You could have just plugged into your streamline equation, like y equals 3x, you can just plug this into this, and you just found that. Instead of going through a slightly more involved integral. But yeah, does that make sense for how to find like a path line? Cool. Same thing. Just dx dt, dy dt. Solve for the simpler one. Find the value. If you can plug it, then if it's in terms of y and x, then you can plug one of them into the other, and then it's the same thing. Find that.
So what if they're the same answer you're saying?
In this specific case, just because we're passing through the exact same like point, and like there's no like time dependence on anything else, it is a very specific case, but you can just see how in like a steady state problem they're like very closely related, especially the passing through the same point. Yeah.
Is that a valid way of solving it if you were given? Like,
Yeah, if you saw this exact setup and you said that
we have to explicitly say that because steady state is when we.
I would just say because going through same point, just give like a little bit of like it's going through the same point, it's steady state, just plug this thing in.
Okay.
Yeah. Yeah, what's up? Oh, so this is just path line. Sorry, I'm not done with the problem. This is the first half of the question where we have to like actually formally derive the path line, because over here we didn't actually have to do that at all. There's no like actual like x as a function of t. We just actually just put some mountains on it because of the nature of the question. So there's no path line here. Oh, we will. This is just path line. I will do streak line like immediately right now. So this is path line. It's different. So again, the streak line equation was v over u is equal to dy dx. These are two different equations. Okay, and now for the path, the streak line. The reason I did the path line first is because it's this way to derive the streak line is very much related to how you're looking at the path line. So now instead of doing an integral from an unbounded integral, we will do something similar to here, where we do a bounded integral over 2 points of time. So then that would give you, double check. Yeah, so then that will give you a, so suppose I'm just gonna move this part over here. So now you'll have a half, but so what we do x naught to x and x dx is equal to t naught to t of a dt. And then you do the same thing, you go through the now the integral again, but now this time you get a half x squared minus half x naught squared is equal to a t, yeah, a t minus t naught. And now you would plug in your this thing, your x naught as 1, and then you would basically find this yeah. Right, so then you everything outside x is equal to a t minus t naught plus x O squared, or we can put, what is that, x O 1, it says half then, or I guess you put the 2 here, put this, and then you just do a big root. Cool. And then the way the streak line works is that you're starting at different initial conditions. So based on what, like, based on like the conceptual definition of a streak line, this, you can see this, right? I don't know if, oh, we're good. Okay. The way what varies in the streak line is when you start off that point. So think of like just a fluid flow just in a tank, and you're just, there's like a dye, like there's like some like little dye that's being added to the flow, and that's like what conceptually a streak line is, right? So when that dye is being added, the t naught time is what's varying, because like the dye is being continuously added. So at t naught, one like drop of the dye will be added at t1. Then the next time another drop of the dye will be added. So that'll make this term vary, and then based on like what actual time in the flow it is, this you have a function of time after that. Yeah, so that is the that's how you do the streak line for x, and then for y, same thing. You can now use, so over here you'd use this equation here. So you'd use this equation. So you would have to have plugged x into this thing to get this type of equation, and then you can do the exact same thing. So let's do that. How does this work? Okay. So this just becomes, I'm gonna skip actually we'll try not to skip too much ahead. Y over y naught. So you're gonna have ln 2 a t plus 1 over 2 a t naught plus 1. Yeah, and then you'll get y. Once you do all the same algebra, you get y is equal to 2a t plus 1 over 2a t naught plus 1 to the half power. So that's what that's going to look like. So the difference is, in this case, you're just doing an indefinite integral, and then you're just plugging in these points in later. This time, since the start time of the particle it varies, or that's like the point of the streak line, the start time of the particle varies, you have to set like specific bounds for t and t naught, and then you can solve the entire thing. Yeah.
When we're thinking, when to use tau?
For the streak line, so like when you're using, it should be tau, or in the way they explain it, all the notes and everything, it's a tau. So you can, all of these t's, you can just put a tau instead. That's just what it's just like a function of tau instead of t, just to signify that it's not like normal time. It's like this for the streak line. It's a little bit weirder. Yeah.
So for the general y, you substitute the new t minus t naught x in, right? Not the-
Yeah. So this would look like, no, this x will stay the same. You don't substitute that one into this thing. This thing will be the same as this thing, because you're just trying to find an expression for y without x. So that's what the point of like putting it in this form is. So you start from here, and then you'd go and do everything else. The times thing. We should probably not. Yeah, what's up?
If the whole purpose for you, first the EW integral and then the definite integral, just because you want to find the relationship to y and x.
Yeah.
Once you have the, we need to get expression for x from the definite.
Yeah, basically, if your end goal was to find the path line for the streak line, yeah, this would the point of this thing is to get y in like a more usable state.
How over two.
Okay, yeah. So I plug in this x.
Yes.
I plug that into this.
Why is there an integral on the left hand side?
Oh. Yeah. Okay.
Is that entire word practice all like
Yeah, so I mean, yeah, so I like again we did this is like half of this part is just doing the path line. This would probably be a separate like subsection of your problem or whatever, is doing the path line. And then from the path line, you see this in the homework, you can just take the same part, like the same dx dt stuff, dy dt stuff, and just put bounds on your time or your tau, and then you can figure out a path, a streak line.
Oh, yeah. Oh.
Cool. Does this make sense to process? Again, a quick summary. Streamline is going to look like that. Move stuff around, separate your variables. Path line is going to look like this, like this. You're going to have a dxdt, dy dt. If one is more complicated than the other, solve a simpler one. That'll probably, in the context of an exam, help you solve the other one. It won't be something like super impossible. Other than that, for a streak line, take your same whatever integral you're about to do for your path line, instead of doing it like an indefinite one, just put bounds on it for your time. And since you have a time bound, you gotta put an x bound as well. Yeah, does that make sense? Any questions? Yeah, what's up?
So T0 is T0 given in this case?
So T0 is let me quickly double check what the solution says, but
Which one, which T?
is like the variable, yeah,
Yeah, which T like the
so they're both like tau naught. Just okay, wait, before I say anything else, I can just quickly double check. That's for sure. Can you open the font? What is the signing for? There's like the tau, there's a tau knowledge, so we can look at actual variables around tau number down. Is it? Okay, cool. Okay, that makes sense. Okay. So then which one is which one is like very in like one of them like is x a function of tau or is it a function of t then?
No, like, you just replace the bounded integrals with tau.
Okay, but conceptually, is that like what's changing then? Is the tau not or the tau changing? Okay. Yeah, what's up? This one?
Yeah, like the very right.
Oh, sorry. That's my handwriting. Is a 4. Because you plugged in like this 2 squared. This x1 is 2, so 2 squared is like 4.
Okay,
So, yeah, sorry. Okay. Let's go to the Reynolds transport question. Oh, sorry, yeah.
Do you know anything about?
Let me get, let me get back to you at the end, so we can go, but I will answer that question. Quick. So suppose we have, no, no, no problem, it's not a problem.
Should be.
But you wanna, I mean,
No,
is it a rental transfer problem? Oh, no, it's like a moving control volume
I mean,
separate.
it is, though.
Oh, it is, would you rather me do like a general, us do like a general Reynolds transfer problem, or do you wanna do like a? The homework 6 question, or is this question?
I will be honest, though. I believe that the general problem is more though.
For the ODK, the moving is not gonna be
Like, I told you specifically, almost in question 2, the V in the first term and the V in the second term are different. For the ODK, we're not.
does that change any of the answer? Does that answer my homework answers?
Should we do that?
Huh?
Should we do the general?
Okay, we'll do general. Yeah, good. Okay, so suppose this is like you have a pipe flow. Okay, so you have pipe flow with one section here. Okay, cool. So now there's a flow coming in here, coming out here. The basic question is, suppose you had like some bolts here, like a big or a big thing which is like blocking this from moving around. What horizontal force must you apply to suppose flow coming in, flow coming out this way? What horizontal force must you apply to like this section over here? To be able to like for it to not to move. So let me give you a few questions. Okay, yeah. But A is equal to 0.01. All the everything here is going to be in like metric stuff. So is that might be a bit okay. Here's fine. Someone complains. I can write it a bit more neatly, but 0.005. Where what else do I know? Okay. So there is also a pressure on this side equal to 1 kA, and a pressure down here which is equal to, oh wait, this is actually 2.01. Get this one up here. It's equal to 323. Is that all the information you need? Oh, you need to alpha. Okay. Let's just set which angle is going to be alpha. Let's set this angle to be theta, let's say. How would we now, do we like a speed in this thing? Fine. Let's see. Okay. 4 meters per second coming in. That's all you need. Okay, cool. Yeah, that should be everything you need. Just take, it's already 51. I'll just give you like 2 minutes. Write down what you think would be like the right set of steps to solve this question. And then we'll just go over it.
Is that 4 meters per second?
Yeah, 4 meters per second. Sorry, if anything is confusing, I'm really sorry about my handwriting. Oh, I'm kind of hard for people.
Sorry, what are we solving for?
You're solved. Oh, sorry. Force. Sorry. Fx required to keep the height stationary. My bad. So you have water coming in this way. There's going to be some retaining force here. Just what's the Fx? Maybe you can find for the vertical force later, but this is 323 and this is 201. Oh, it's steady. Also in general, if something is not given explicitly in time, it's going to be a steady state problem. I haven't mentioned it here, but as a general rule, steady state, if it'll assume a steady state unless specifically said otherwise. So this is also steady state. I could just mention that as well. One more minute to figure out. Okay, cool. So let's get started on this. What do we think is the first thing we should do? Suppose you got the tiny question on like a exam. What's the first thing you should solve for? Yeah. Yeah. Oh yeah. That's right. I went a little bit ahead of myself. We should probably draw a control line for this thing. So maybe the way to track it. What's the cover try to draw a control volume? There's a very specific way it has to be drawn. That's why I'm trying to make you guys do it. Anyone come up? Here. Let's draw a control line for us. The rest fit inside as well. Make the rest fit outside. Oh, it's inside. Oh, it's like that.
That's what I was wondering.
Yeah, it should be the inside, right? Cover the entire thing. Yeah. Thank you. Okay, so the reason that this you want to draw the control volume like this is because you want to, I mean, like the angles will come into play later, but this simplifies in the sense that you're on this boundary of your control volume over here, your flow is like perpendicular outward, so you're not worried about like it coming in at an angle. So when you have your, remember there's like this like V dot N term in your Reynolds transfer theorem. This, when you dot product, when you get the dot product, this dot, like this being 1 or like it being in the same direction, this simplifies this part of the equation. So you don't have to think about that. It's really neat to think about a velocity or like a angle at some point, but at least for now, this simplifies that kind of analysis. Okay, so the first thing that we're going to try to do is find the velocity coming out here. And this one doesn't even really require like an explicit Reynolds transfer theorem. You could just say that and if we want to say that it's incompressible, let's go. We have rho, that's a 1, 2. So when I say A1, A2, that's what it means. Rho A1, V1 is equal to rho A2, V2. And we know that the density is constant, so these come out, and you can find V2 as just A2 over A1, V1. So then what would this be? Let me just open it so I don't do the math.
Excuse me. Hello?
Okay, cool. Yeah, so if you did this thing, you'd get V2 is equal to 16 meters per second. I probably could have done that without having to open my notes, but
It's A1 over A2.
So it will be.
Oh. Yeah, you're right. And you'd get V2 is equal to 16 meters per second. Cool. So, and why do we need this? Just like, why did we have to solve for this thing? Yeah, because there's a max flux, like a momentum flux in, a momentum flux out, and the momentum flux out requires you to know your velocity coming out. So that's what you have to do. Okay, so let's go to the next part. Let's look at the horizontal linear momentum equation. So you have f of x is equal to, anyone can tell me if I'm doing something wrong. E dt of rho, I'm gonna say it's u for the momentum and for the horizontal velocity plus CS what is this, rho b times b dot n, or I guess u. Okay, yeah, this is what it's supposed to look like. Okay, so the first thing we can say is that, well, I guess these come out. You don't really need the. Actually, no, you do need those. Sorry. You do need those over here. I'll add the density later. It was like 1,000 kilograms per cubic meter for water. But yeah, this first. The first thing we know that this is a steady state problem. So this time variation can come out of the picture. So now we have a basic, yeah, there's also, you guys will learn this in lecture where you also have to account for the pressure forces on the sides. Does that come into play yet? Okay, cool. So there's also, I'm gonna call it F pressure on from the other side. I'll keep on this side for now. If my signs go off, we'll change it. Okay. So the first thing you'd have to do is find the momentum. So this can now be thought of as the integral over the first section, b dot n, plus the integral of the second section, rho u b dot n. Okay. So the normal force coming in, so we have velocity. We'll put it over here. You have a velocity coming in, but your normal force is acting out. So your dot product on that thing will be a negative. Might be. Okay, might be like this. Higher thing over this. It might look like this instead. Wow. Okay. So the first thing you know that this let me put the back in here. So you have your v dot n. So this is just going to be your momentum coming in. So that's just going to be that's going to be negative, yeah. So you'll have, and then your v also in that direction is the same, 4 meters per second. So that's gonna be, what's this? Rho. Probably be 1 squared. Takes a rho, V1 squared A, because you're taking your integral over your first surface, so you have to put M as a uniform flow, so you just multiply by A. And then your second one will be a rho or rho, what is this? Let's figure out what this angle is of this velocity. So you gotta find the horizontal component of this thing, right? So that's the same theta. So it's a cosine, right? Yeah, it's a cosine. Okay. That's rho, what is this? Rho U, oh yeah, rho V, and then we can write that the U coming out this way is just over here. U is equal to a V1 cosine theta. Yep. So then you get, yeah, V1 squared cosine theta, because this is positive.
Why V one and not V two?
Because the relation between, that's right, no, you're right. 2 squared. Oh yeah, no, you're right. Now, and then that's with the angle theta. Okay, cool, yeah. Okay, so then that's how you would do this. Oh, it's 703. Okay. So then the next thing you'd have to do is you'd have to add your pressure stuff. Okay, cool. So yeah, what's up? Oh yeah, wait, let me double check.
But the flow is coming out, so coming out is positive.
Yeah, I mean, yeah, so this part is positive because it's in the same direction, but he's asking if this U, since the U is technically in the negative X direction, should that be negative? Oh, yeah, so the sign should actually be the same. Okay. Did I do that wrong? E2 mass. Okay, fine. Yeah, so this actually should be negative because this is in the negative X direction. So this U is going to be negative V2 cosine theta. Sorry about that. Okay, here we go. Yes, okay, cool. Now you have fx plus, what's up? The area. A2. And then this is plus P, this is plus a P2, where's this at? Plus a pressure coming in over here. And then a pressure coming in over here. The same thing. So is this the same? Let's think. That's also at an angle theta. That should be fine. So then we have, what is this? P1A, because that's the same, just horizontal direction. But this pressure is going in the same direction, so plus P2, P2 cosine theta, A2. Okay, so then solve this equation. And you should find the answer. So what is this? We have all the stuff for this thing. Yeah, go now. We have to isolate this thing. And then that should allow you to find your answer.
Is P1 and P2 gauge pressure?
Yeah, these will be gauge pressure, but also since, yeah, these are gauge pressures, yeah.
If it weren't, would you have to take into consideration atmospheric pressure at other points or?
If you have to take into consideration, absolutely. Oh, and yeah, if there weren't gauge pressure, then you'd have like a lot more like atmospheric pressure coming in. That would, but since these are gauge pressure, everything's like equalizing, yeah. Yeah, so it's negative because, so this U is in the negative X direction, right? So right now we're defining X over here and Y over here. So we're defining X to be in this direction. So this velocity coming out, so it's this term, the V dot N term in any of these momentum stuff is telling you that it's either in or out. That's all this, the sign here is just telling you if it's a influx or outflux. But this, since this U, like the actual term, is in the negative X direction, you can put the negative sign on it. I'll post pictures of the board, so just find that. We've run out of time here, but I'll post a note which will, if I've said anything wrong or like weird here, it'll clarify that. Yeah, I might have said something wrong too. So. Yeah, don't worry. And then we'll go out and we'll actually see. Yeah, what's up? Yeah. So you solve for this thing, and then it's just, and either you're figuring out the pressure that's the bolt field, or you're figuring out the pressure of the water. This is the pressure of the water feels. So if you want to figure out the pressure, the bolt, because it's like the equal octave reaction, you just put a negative sign on that.
So is there like here, our U should always be either in the direction of X and Y. Our V will always be in the direction that's right. Perpendicular to the third, because we're not considering alpha as in the X direction.
Yeah.
It's like my conclusion here is we are this equation is all in X direction.
Yeah.
So here we V dot N, but this V dot N is given a scalar, and that scalar is all perpendicular to the start, but not in an X direction.
Let me quickly check the